כן. לא, כי אני לא ידעתי אם זה סגור, היא זרקה לי, פגשתי אותה לפני שבועיים, היא זרקה לי עכשיו, לא הייתי בטוח אם זה עכשיו סגור. טוב, מזל טוב. אז יעל גם טוב, אז יש הרבה אנשים. אוקיי. טוב, אז אני אדבר איתם. כן, כן, כן. אוקיי. הם יודעים, זאת אומרת? הם ידעו מה יהיה?
יש, לא בטוח למה היה, למה היה, בטח להגיד שיש רשימה. הם לא בדיוק, הם לא מושג, אבל יש רשימה מה יש לנו. עד המורל, אם לא, קיצור, צריך לראות. מה אתה רוצה לאחור?
בעצם פנקציה, כן, כן. זאת אומרת, אתם עשיתם את זה,
לא, זה יהיה.
כן.
אתה יודע לעשות לראות המקולה?
לא ברמות, כאילו, זה הדברים בסיסיים, אבל עשיתי קורס, אתה יודע.
לא קורס, אין לך ניסיון.
לא, אין לי ניסיון. עשיתם PCR'ים שאני מוצא אצלנו במעבדה.
צריך לראות שיש לנו מה שמתאים לנו, לא בטוח, נעזור בזה.
אבל זה מסמן לפריטים זה כזה, נכון?
תהיה מדהים.
אוקיי. ועשיתי טומטו, לא מסמן לפריטים?
עשיתי טומטו. תראו, כן, מקום לא פרסמנו שום דבר, היה לנו הצלחה פעם. אבל
אני רוצה לדעת, אני מסתכל על אינטראקציות, זה חשוב
זה לא יודע,
כן.
אני לא יודע אם יש לנו את הרעיון בטוח לייב זה בסדר, אתה עושה אינדורו עם זה.
טוב, לעשות איזה עכבר ולראות איך רואים, מה הרמה של הפירוטנציה.
כן.
אוקיי.
לדעתי אתה צריך לבחור עכשיו אני לא יודע, אבל לא יודע איזה קומות או איזה קומות, כל השנה צריך כמו בחדש. הכי טוב שאני רואה זה לעשות את זה עם הקג. לעשות, להחליט האחווה שלך עם האחווה של קורטר, של מים. ואז להזריק לאנטי-פרס. ואז תקבל מלא טעים עם אחלה אקספרשן באדנדרית.
אוקיי, אז יש לכם את האחברים?
זה יהיה עיניים, יש לך. להחליט אותה, ג'נוטייפינג, כל משקל.
טוב, בסדר, אני מדבר, אני יכול, אני אעשה איזה פיילוט, אני רק תקל בבעיה, אז נעבור לתוכנית אחרת. זה אם שוב, לאגנטים להחליא אפשרי. זה יש לי שם כל כך הרבה מושבות, אני לא משתלט על זה. אני לבד פה ואני מתחרפן כבר כמויות החברים שיש לי שם.
אוקיי. לא רק מייל, גם רעיון איתי. קיבלתי את זה. הרב בלח.
אוקיי, אז אני אתחיל בזה.
עדי, אתה יכול בבקשה ללכת למשרד להביא בטריה?
כן.
Okay, so this is we stopped last time. So eventually we'll find that what limits sensory perception, our ability to discriminate between different stimuli, is noise. And we started talking about in which way noise limits performance. So the first half of this meeting we'll talk in details about how to quantify the effect of noise on sensory perception. And my comment at the end of last lesson was that last lesson was that spatial and temporal filtering are good in the sense that they reduce noise. Okay? So by integrating information a little bit over space and over time, you reduce a bit noise. So from here now we are going to talk about noise, and I started discussing these data that come from an experiment for determining interoral time differences. So just to, since in the last presentation the experiment itself was unclear, I brought this figure that we'll see again when we talk about the auditory system. So suppose you have a sound source somewhere in space. Okay, we are talking mostly about azimuth, not about elevation, so we are talking only about this angle. And if it plays from the right side, you will have different stimuli, different sounds arriving to the two ears. The right ear, here in red, okay, the right ear will have a sound that is louder because the head acts as a shadow, and it will be also earlier because it is closer to the sound source. Okay, so we are talking about interoral time differences, the fact that the sound in the right ear here is earlier than in the left ear, and interoral level differences, which refer to the fact that the sound in the near ear is a bit louder than in the far ear. Okay, and we are sensitive to these differences between the two ears. In the experiment that I'm going to show, the interoral level differences were set to 0. So instead of playing the sounds from a loudspeaker out in the world, the sounds are played from earphones. So you have two earphones, one in each ear, and you play the sound with this type of phase shift. Okay, so the thing that varies in this experiment is the time delay or the phase delay. These are pure sine waves, so time and phase are almost the same thing. And this is what's plotted here on the x-axis. Okay, 0 means that the sounds are playing in such a way that the sine waves in the two ears are in phase, the peaks are at the same time and valleys are in the same time. And as we go into the positive direction, the one of the two ears, the reference ear, usually the ear on the side of the electrode, is earlier, and as you go in this direction, the other ear is earlier. And as you see here, as you go over a cycle, firing rate changes by a lot. Cycle here, I told you this neuron has a best frequency of about 400 hertz. So one cycle represents a time shift of about 2.5 milliseconds. So as you shift the time of the peak of the sine wave by one cycle by about 2.5 milliseconds, you get a relatively strong modulation of the firing rate. Now, how this happens is something we'll study when we discuss the auditory system. Right now, what I want to do is to discuss stimulus selectivity in terms of neurons using this example. Okay, so what's the stimulus selectivity here? You have the peak at about, I don't know, 200 microseconds. What would be the resolution of this neuron? How well does it broadcast the information about the ITD? How would you measure that? What would be the So width, yeah, the width of this curve presumably is represents the precision at which you signal the fact that there was an ITD at 200 microseconds. Now, it turns out that if you look at what an animal does in the world, again, we'll discuss it when we discuss the auditory system, neither of these measures make sense, and the reason is that the animals really experience this range of ITDs. This is guinea pigs. They have small heads. The delay between the two ears is not very large. So neither the peak response nor the width have any relevance to the ITDs that the animals experience in the world. On the other hand, what you do see is that there's a steep change in the firing rate, and this steep change in the firing rate falls within this ethological range. So if anything encodes here the ITD, it's really encoded by being high when the near ear, when the ear has the earlier sound, and low firing rate when the ear has is delayed relative to the other one. Okay, now the half width here, by the way, is about 500 microseconds. Okay, you can look from the scale. So we have about 500 microseconds. This sensory resolution of animals, okay, and of humans is in the range of tens of microseconds. So it depends exactly how you do the experiment. We are better in clicks than with pure tones. If you do pure tones, it turns out that it depends on the frequency. We are sensitive to phase difference, not to time difference. There's a lot of subtleties here, but the important finding is that humans can do at 500 hertz ITDs of 50 microseconds with clicks that they can do 10 microseconds, and that's about as well as other animals do. Okay, what? Microseconds, not milliseconds, microseconds, okay? We can discriminate between two clicks which are with ITD of 0 and clicks that come with an ITD of 10 microseconds. What's the width of an action potential? So in the central nervous system at physiological temperatures, the width of an action potential is something like 300, 400 microseconds. Okay, still, we are talking here about time differences that are substantially narrower than the width of an action potential. Okay, so how do we want to study this question? So when you have in human psychophysics, the typical experiment to measure sensory selectivity is an experiment with two alternatives, two interval force choice. It's written in many different ways. You hear two sounds. One of them will be the straight ahead, the other one will be shifted to the side. They come in random order, and you have to say which one is to the left, or which one is to the left among the two that you hear. There are all kinds of versions of that. And so this is what a human does. You hear two sounds, one interval, two interval, and you have to say whether the right one was the first or the second. Okay. Now we want to do the same thing with the neuron. Okay. So the way to do it with the neuron is, in this case, I'm going to discuss a version in which the neuron fires to the first stimulus, to one stimulus, the neuron fires to the second stimulus. You're being told how many spikes occurred, and now you have to guess which stimulus occurred when. Okay, now the assumption is that you know how a neuron would respond to the two stimuli. Okay, so you have the assumption is that you have perfect knowledge of the statistics of spike counts. So you know that if the ITD is 0, You know that the distribution will be one distribution, and if the ITD is 100 microseconds or 50 microseconds, then you're going to have another distribution, and you know these distributions, okay? This is why these calculations are sometimes called ideal observer calculations. Okay? So, and there are many different variants of this. Okay, we discussed that. Okay, so the basic intuition that you have to come out of here is that if the exercise is done in such a way that there's a small amount of noise on the average values, okay, then it will be easy to do the discrimination. Okay, you will have easy time saying which stimulus was which, whereas if there's a lot of noise, you can't. Okay, but we want to quantify this, so these are real data. Okay, these are histogram of spike counts evoked in a neuron in guinea pig, inferior colliculus. Blue come from 100 repeats of a stimulus in which the ITD was 0 microseconds, and the red from 100 repeats of the same frequency with ITD of 100 microseconds. These experiments were run by Trevor Shackleton and Ellen Palmer in Nottingham about 10, 12 years ago, and they gave me the data. We analyzed this data. They published a couple of papers on them, and then we did some more analysis on them using mutual information and Fisher information and all kinds of things. So there's a small paper that came out of it. But here, these are real data. Okay, these are histograms of spike counts that were emitted by a real neuron in a real animal. It was anesthetized, but still a real animal. And if you consider guinea pigs to be real animals. So, what? It's the inferior colliculus. It's a station in the midbrain. Again, we'll discuss. No, it's auditory. The superior colliculus is visual. The inferior colliculus is a very important auditory station. Yes?
So how can we be sure that this particular neuron or this particular set of neurons was the most finely tuned to, say, this particular task? Could it have been that there are other neurons that are responsible for the behavior?
Of course. I mean, it could be that I put my electrode in the wrong place. Right. However, as I will show you, I mean, I have two arguments for that. The first one is that, as you will see, this neuron is actually, that's one of the typical best. It does almost as good, not as guinea pig, but as human ITD discrimination. Okay, it's actually, it does extremely well in terms of doing these these ITD discriminations. The other one is that it is known that if you hit this place, this location in the brain, then you lose your ability to do these tasks. I mean, it's an obligatory station. All the information from the brainstem to the forebrain goes through this station, this inferior colliculus, and it is known both in humans and in animals that if there's this region doesn't function correctly, then you can't do these spatial discrimination tasks. Okay, so there's good evidence that the neurons there really participate in the task, as good as you have for any participation of any brain region in any sensory task. Okay, so eventually I want to excuse me. If you have questions, please to me. Okay, I don't mind you reading papers and eating, but I do mind if you speak among yourselves during the lesson. Okay? Yeah. 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 These are data. Okay, I have 100 repeats of the 0 microsecond stimulus and 100 repeats of the 100 microsecond stimulus. Okay, and these are just histogram of spike counts. Okay, these are data. Okay. Now, in order to do the two alternative force choice, I'm going to take a detour. Okay, so first of all, I'm going to do a different type of task. It's a one-trial decision. You hear one sound, and you have to guess whether it was 0 or 100 microseconds. So you get the spike count. Okay, you know these histograms. These are given to you. Okay, and now I present a sound, I tell you there were 9 spikes. Okay? Was the sound at 0 microsecond or at 100 microseconds? You have to decide. Okay, so this is the one trial decision. Okay, so how will you decide? What are the, so first of all, we have to define a decision rule, okay? What is a decision rule? You are given the spike count and you have to decide. So how will you decide? What? According to the spike count. So basically, you have spike count 0, 1, 2, 3, 100, and you have to say for each spike count, you say if this occurred, I say 100. If another one occurred, I say 0. Okay? A decision rule is really an assignment rule that for each spike, that assign to each spike count that you observe one of the two stimuli, your decision. Okay? That's the only thing you can do. Okay? That's actually, if you will learn statistical theory, the class of decision rule is slightly larger. You are also allowed to make a decision by throwing a dice. Basically, decision rules are simply assignment functions. Okay? Each spike count, whether it was 0 or 100, what's your decision? Okay, so let's look again at these histograms. I observed spike count between 0 and 11, and how do I assign a stimulus to each one of them? Okay, so for example, 11. If I counted 11 spikes, 100 for sure. Why? Because 11 never happened when I presented 0 microseconds. Okay, that's easy. So 10 too. I mean, it's obvious that my decision rule will always assign 10 and 11 to 100 microseconds. Well, the overall errors are going to depend on the probability. In this experiment, I assume for simplicity that the probability is 50%. Okay, but for the type of calculations we are going to do now, it's the number that I come out with. This is unimportant. The question of the probability will come out a bit later, the probability of the stimulus. Okay, so assume that this, suppose that this is now my decision rule. Okay, if I see 10 or 11 spikes, I say 100. All other spike counts, I say 0.
Are you the experimenter or the animal? The one that decides?
I'm observing the neuron, okay, and according to the neuron activity, I have to make the decision. Now, behind that, there's the belief that it's not me who makes the decision, but the higher brain areas that make the decision. Okay, but here it doesn't matter that there are higher brain areas. Okay, I sit, I observe the spike counts, and I make the decision. Okay, so this is the basic. This table is the basic thing, basic creature that we are going to analyze. Okay, suppose 0 was presented. My decision rule, if 0 was presented, I will always say that 0 occurred, and I will never say that 100 occurred, okay, because the way that I selected my decision rule. If 100 was presented, then if there were 10 or 11 spike counts, I will say 100, but they occurred only in about 1% of the cases, and in all of the other cases, I will say 0. So when 0 was when 0 was presented, I will be my decision will be correct always. When 100 was presented, I will make a lot of mistakes. This is for this decision rule, specifically for decision rule. Okay, so I'm using, in the slides, I use the terms false alarms and detection rates. The idea is that 0 is the default, okay, and 100 is the exception. And so if I say 100 when there was 0, I raised the false alarm. These are terms that come from the technological application of this theory, and they have to do with the fact that it was developed during Second World War to analyze radar signals. Okay, so as you will see, the main creature that we are going to calculate out of that is called receiver operating characteristic, and the receiver is the radar receiver. Okay, that's the origin of the name. Okay, so we have the load detection rate for the 100. Okay, and now the question: how do we proceed? How do we modify? Get another decision rule that will be in a sense will be better, or that will increase the detection rate of the 100 microseconds. Okay, so I have to select one of the other spike counts that may occur between 0 and 9 and assign them, move them from the class of 0 to the class of 100. Okay, and I want to increase the detection rate of the 100. Okay, but I don't want to hurt this 0 much. Okay, so what I want to do is to increase the detection rate of 100 and increase as little as possible the false alarm, the detection of 100 when 0 occurred. Okay, so what are the numbers that are going to go into these two cells? Okay, so suppose that I am assigning now 8 to 100 to the 100 class. Okay, so these are the number of times. That's the probability of seeing 8 when I presented 0, and now they are going to be I am going to decide that they were 100. Okay, so this bar is going to add up to that place. Okay, and the corresponding red bar is going to go into the 100 cell. Okay, that's clear. Okay, so now how do I what?
8 and 9.
No, in this case, I'm presenting a decision rule in which 0 up to 7 and 9 are assigned to 0, and 8, 10, and 11 are assigned to.
So the 9 is supposed to be 0 or between 0 and your parameter.
What?
You said 0 was presented in the lines in your table.
What?
When
When 0 was presented, my spark counts follow the blue histogram. Okay, so if I assign 8 to the class of 100, okay, then 0 was presented, but I said 100. Okay, so that's a probability. The blue bar is the probability of saying that 100 was presented when 0 was presented. Yes.
How many neurons?
This is a single neuron. I presented to it these stimuli 100 times each, so I have these are spike count histograms that come from one.
If there's many neurons, you can get much.
We'll talk about many neuron in a moment. Okay. At the moment I'm looking. I mean, the game is. I specifically said that I'm looking at a single neuron. Okay. The game is on a single neuron. We'll see what happens when there are many neurons later. Okay, so the idea is that I want to make this large, this small. These are the bars, so I want to use the spike count where the ratio between the bars is the largest. Okay, so here are the ratios. This is red divided by blue, that's 12 here, it's 6 here, it's 10 here, and so on. Okay, these are called likelihoods. Okay, these ratios. Likelihoods. In Hebrew, it's nirut. Okay, these are the likelihood ratios. The ratio of the probability to see 100 relative to the probability of seeing 0 when I observed a certain spike count. So the likelihood is high here and become not monotonically, it becomes smaller as I go to the. Okay, so obviously the spike count with the largest likelihood is 9. So 9 is the next one that I'm going to assign to the class of 100. So my next decision rule is that 0 to 8 are called, I decide 0, and 9, 10, and 11 I decide that there was 100, and then I increased my false alarm rate, saying 100 when there was 0 to 2 per mil, but I increased this one from about 1% to about 3.5%. Okay.
Should I call 100 millisecond your alarm?
100, it could be the reverse. Okay, here the situation is symmetric. Again, the terms come from a situation in which it is not. Okay, in radar, most of the time you don't have an airplane, and sometimes, rarely, you have an airplane. Okay, so saying that there was an airplane when there was not an airplane is a false alarm, and saying that there was no airplane when there was an airplane is a misdetection. Okay, this is where the terms come from. In statistics, these are called type 1 and type 2 errors, which is even worse. There's no real null hypothesis. There's a symmetry here. In null hypothesis testing, you have an asymmetry between the null hypothesis and the alternative, and here there's no symmetry. Okay, which will be the next one to assign to 100? If 3-point detection rate of 100 at 3.5% is still too low for you, what would be the next one that you will assign? Okay, so you see that you get this type of funny decision rule where 0 to 6 and 8 are assigned to 0, and 7, 9, 11, 10, and 11 are assigned to 100. Okay, so these decision rules come from the theory. They may occur. Okay, so if you add 0, then you increase this number to 1.6%. This one already goes to almost 18%. Okay, and so on. The next one is going to be 8, and so on. Okay, so the end result of this calculation is that I have a lot of different decision rules. Okay, and what I'm going to do is to plot all of these, the performance of all of these decision rules together on a single plot. Okay, so I'm looking at the probability of saying 100. Okay, on the x-axis, I am looking at the probability of saying 100 when 0 was presented, so I'm plotting the value of this cell. Okay, on the y-axis, I'm going to plot the value of this cell. Okay, so I'm plotting them against each other, and I get a curve because of the way that I selected them with the biggest ratios first and then the decreasing ratios. I'm going to get a curve that's always, is this convex or concave? This is what mathematicians call convex, but I think that a man from the street would call it concave.
Man from the street will not call it.
The ka'ur or kamur?
Yeah, I know.
Anyway, so the blue line here represents the data that you've just seen. Okay, this is this curve that represents all the one-trial decision rules that I can get. And in addition, I drew two limit lines. If the two distributions are identical, okay, the probabilities of seeing all the likelihoods are 1. All the probability of observing 9 when 0 and 100 is the same, or the probability of observing 7 is the same, and so on and so forth, then it's easy to see that what you are going to get is you are going to live on the diagonal. So the red line, if the two distributions are identical, if the red and blue distributions are on top of each other exactly, okay, then the values here and here will be always the same. Okay, so you will end up being on the diagonal, and if the two distributions are such that they are fully separated, no values can occur with non-zero probability in both of them, then you're going to get something that looks like the green curve. Okay? Yes?
So a question, usually in psychophysics when you try to get information in order to plot them, our teachers, you manipulate the criterion somehow.
Yeah. This is what I do here, okay? The parameter is the criterion.
Could you give an intuition of how the different conditions?
How to select the criterion?
No, how the different conditions affected the subjective criterion, like in the slide before.
Okay, so the selection of the criterion is the specific decision rule that you are going to use. Okay, in psychophysics, the question is which one of these decision rules I want to use. Okay, that's a decision rule that makes you detect a lot of 100, but then you will also make a lot of errors when you see 0, or a decision rule in which I don't want to make any errors when I see 0, but then I will also miss a lot of the 100 presentations. Okay, so that this neta, okay, has to the decision. Which decision rule the selection of the decision rule will be influenced, among other things, by the probability of the two stimuli. Okay, so for example, in radar, you will usually use decision rules that makes you make very few mistakes when you see 0, when there's nothing. Okay, because you don't want to shoot your missiles at nothing. Okay, you want to be very sure when you shoot a missile. Okay, so you're going Kipat Barzel, yes. So you will use a very conservative decision rule. What?
You also don't want to meet.
Yeah, so what you want is two distributions that are very well separated, okay? But you will usually put your threshold in such a way that you will not do many false alarms. Okay. On the other hand, under other conditions, you will allow yourself to make a lot of false alarms. For example, well, I don't. All my examples come from the current security situation, so I'm not going to. I'm not going to give one.
You can say something about the hurricane.
About what?
The hurricane.
The hurricane, okay.
Where false alarms are okay and
false alarms are okay, but misdetections are very bad. Yes. Oh, I know what No, it's actually a good example, not the hurricane. The story of this Italian geophysicist who got sentenced to prison. Okay. That's actually not a bad example. They should have taken allowed themselves making false alarms, because misdetection in that case meant that 25 people died. Okay, so they were sentenced to prison for not choosing a decision rule that was.
There might be an earthquake somewhere in the next few weeks.
Yeah.
That was what expected. That was what they could say. That's all.
Okay, let's continue. So we started with the two alternative force choice tasks. What's the relationship between the hour seekers and the two alternative force choice? It turns out that the decision rule for the two alternative force choice is that I have one spike count, second spike count, okay, and I will choose the likelihood, the interval in which the spike count occurred with the larger likelihood. Okay, so I'm observing the likelihood of the first interval, likelihood of the second interval, and I will say 100 in the interval where the likelihood was larger. Okay, now in a way that's as if you made a one trial decision where you used the likelihood of the response to the first stimulus as a threshold for the decision of the second stimulus, and it's easy to see. You don't have to prove it, unless you really want. You don't have to make to write the proof. But once you realize that, it's easy to see that the probability of correct response is the area under the ROC curve. Okay, so in the two alternative force choice, in the red case, okay, the probability is, you don't have any information in the response. Your probability of making a correct decision is 50%. Okay, if you have fully separated distribution, your probability of making the decision is 100%. Okay, because each value has a clear class to which is going to be assigned. And in the blue case, which is the one that we analyzed, you will be between the two. Okay, the area under the ROC curve. ROC. ROC is receiver operating characteristics. As I told you, this comes from radar, the receiver. Okay, now, in fact, in the experiment, Trevor Shackleton and Alan Palmer repeated the 100 presentation at each of many different ITDs, 21 different ITDs. So I can do the calculation for each pair of ITDs. Okay, I can take the two spike count distributions, calculate the ROC curve, and calculate the area underneath the ROC curve. Okay, so here, for each pair of ITD values, I calculated the histogram, I calculated the ROC and the area under the ROC curve, and the example that I showed you were 0 and 100. Okay, so this is 0 and 100 would be about here. Okay, and this number is more than 0.75. What? Yeah, for each pair of ITD values. Okay, I got data. I showed you histogram for 0 and 100 microseconds, but in fact, I got from this experiment 21 different values of ITDs. Okay, they presented 2,100 stimuli, 100 in each ITD. Okay, it's an extremely boring experiment. I mean, they told me that they hated doing it, but they wanted the data. They have to verify that the neuron remains well separated and the animal anesthetied. I mean, it's not that they press 2,100 times a button. They have a program that runs them.
Even there, they come back after 2 hours.
No, they can't. Okay? That's the problem. And usually, during the experiment, you watch how the responses accumulate. So you know after 200 stimuli, you know how it will look like. Okay, they collected all of this data because they wanted to calculate the ROC curves without assumptions about the distributions, about the shape of the distributions. That's why they repeated so many times the stimuli. Yeah.
The value here is...
So the value here is the area under the ROC curve. When I use, so this value here, I think it's that one. Okay, this square represents the area under this blue ROC curve that I showed you. Okay, and if I would observe the spike count of this specific neuron, and I had to make the decision, and I knew the two probability distribution, then, okay, I would be able to make 78, 80% correct decisions in a 12-alternative force choice. It is symmetric.
No, but why is it not symmetric in the ITD?
It's not symmetric in the ITD because of that. Okay, what you see here in black now is the average firing rate. Okay, plotted as a function of. So what you see is that in this range, the average firing rates are about the same. So if I compare the distribution of at 400 and at minus 400 and minus 200. There's very little difference between the mean. The probabilities are highly overlapping, and so my ability of making a correct decision is weak.
So you can learn about the environment of the
There's nothing about the environment of the animal here.
I mean, the normal.
Why it looks like that? Because this neuron is on that side of the brain. This is on the right side of the brain, so it tends to prefer ITDs where the right ear is leading. There will be a neuron like that on the left side of the brain that looks the opposite. Okay, and then I can ask what is the minimal ITD that I can discriminate using this neuron. So I'm looking at the at these distances. Okay, I'm looking at the first number along this line that is larger than 75%. Okay, this will give me the ITD difference, the best ITD difference that this neuron could discriminate. Okay, and I'm selecting the narrowest neck here. Okay, this neuron does best at ITDs between about 0 and 100 microseconds. So I say I'm selecting the best ITD from this region. The best ITD difference, yeah.
Just to be sure, the X and Y axis are the absolute positions of
the ITD difference between the two ears. Okay, one stimulus has an ITD difference of 0, and the other one has an ITD difference of 100 microseconds. Okay.
How did you say that this is the best?
This is where you see that as you move a little bit in ITD, you get high probability of making correct decisions. Okay, so it can discriminate between 0 and 100 microseconds. Okay, if you look at, it cannot discriminate between 400 and 300 microseconds. Yeah, so again, the color here are the probability of making correct decisions when you have this ITD and that ITD. Okay, so you want to be in the warm color range to make correct decisions. So I can read the best ITD difference that this neuron can discriminate, and these are the values for many different neurons. Okay, I think that specific neurons was that one. Okay, the one that I showed you is that one. Okay, that's the green line represents human performance in a similar task. Actually, using longer tones. I mean, the humans had a slightly easier task here. So you can see that the neurons from the guinea pig, single neurons in the guinea pig I see, do almost as well as humans do in this task. Yeah.
Each neuron is a neuron.
One neuron. Yeah, that's the best ITD for one neuron.
The best ITD, and so which frequency corresponds?
The frequency is along the x-axis. You see that as the frequency goes up, the best ITDs go up as well in a linear way. Okay, and this means that what we discriminate are fixed phase differences and not fixed time differences. But that's a secondary issue here. I don't want to go into it. Okay, so that's partial answer to your question. Okay, you asked, we have many neurons, we could do much better. Okay, the fact is that in many of these tasks, the best neurons do as well as behavior. Now, here I compared guinea pig, anesthetized guinea pig with awake humans, but you can do the same. We might get to later to example in which the recordings were done in a behaving monkey, and so you could compare the responses of the neuron with the behavior in the same session, and you see the same thing. Yes?
Oh, this is best observed single neuron, right? You cannot be sure this is the best.
So this is the best observed neuron, so presumably the best neuron would be better than that. So there are two questions. One of them is why don't we do like the best neuron, which does better than behavior? And the second is, why don't we improve by combining information across a lot of neurons? Okay, so we'll get back to that to these issues in a moment. Okay, I want just let me finish and then I'll take your question. Okay, I want to make two comments here. First of all, when I'm going back to the likelihoods, you can see that good likelihoods, good well-separated distribution should have very large or very small likelihoods. Okay, a likelihood of 0.1 and a likelihood of 10 are good. Both are good. Okay, because both are informative. If you see this one, it's strong evidence for blue, and if you see that one, it's strong evidence for red. Okay, so in order to give the same weight to 10 and 0.1, I'm going to take logs. Okay, so I'm going to look at log likelihoods, and now it's the absolute value of the log likelihood that's the information. Log 10 and log 0.1 in absolute value are the same. Then log of ratio is difference of the logs. Okay, and I want to create, if I want to create a kind of an index of performance, okay, that's based on the likelihood ratios, so one way of doing it is squaring them and taking the average. Squaring the log likelihood ratio, I said that the likelihoods themselves, the ratios themselves, okay, can take a very large positive number and very large number greater than 1, or numbers that are close to 0, but they have the same meaning. So in order to make the 0.1 and 10 same thing, I'm taking log. Okay, now good well-separated distributions, I want now to use the likelihoods to create an index that will tell me whether the discrimination will be good or not. Okay, so I'm taking the likelihoods, I'm taking the logs, they may be positive or negative, so I'm squaring them and I'm taking the average. Okay, this will be a kind of an index that will tell me whether the ROC curve is, I will be able to make good discriminations or not. Now, this looks like what? Physicists in the audience? What?
Entropy.
No? Not the entropy? Okay, it's in a way it's as if I'm taking the derivative as a function of the ITD. Okay, so what I'm doing here is to take the derivative of the log as a function of the parameter. I'm squaring, taking the average. This thing, you will learn about it in עיבוד מידע ולמידה, and you will learn about it in neural networks too. Okay, this is called Fisher information. Okay, so the Fisher information, in a way, is an index of how well your distribution overlap as you change a little bit your parameter. I had a bit here when I calculated the Fisher information. I'm going to skip this. Okay. Let's take a break and then we'll talk about population of neurons.
The analysis assumes that spike counts are what is important here, right?
In this case, I use a spike count as a measure of neural activity. In principle, we use also timing information. If you use timing information, then you can still talk about likelihoods, but now your space of possible responses become much larger, so it's much more difficult to estimate from data.
intuitively, does it seem that it's you can estimate better with spike count, with spike timing and spike count?
So we did, as a rule, for these neurons, timing information is not that strong. There's very strong correlation between time and count information. The earlier responses are also, if your spikes occur earlier, there is usually more of them. Maoz Shamir reanalyzed this data once again. There's a paper with him and me that appeared last year, I think, where he tried to slightly different detection. He has this temporal winner takes all classifier. So he used his temporal winner takes all classifier on this data to show that you don't do better than using spike count, but you do it much faster. Using timing, okay, using the temporal winner takes all. Temporal winner takes all basically is the first neuron that fires. Not the one that fires the most, but the one that fires first. Okay, and it turns out that in this data, the temporal winner takes all does about as well, slightly less. Comparable to the spike count classifier, but since it reaches the decision at the time that the first spike in the population occurs, it does it very fast. Okay, so that's a way of using temporal information even if they don't improve your detection. In this data, there are other data in which temporal information is much important. We analyzed cortical data. It's a paper that appeared in 2005, I think, in Journal of Computational Neuroscience. I tested the spike count code, kind of the latency code, and the combination. And I compared it with my best estimate of the information you would get from the full spike pattern. And it turned out that spike count alone don't do it, spike latency alone doesn't do it, but if you use it combined, the two-dimensional spike count, spike latency, it does as well as the full spike pattern. The problem is, I was interested in this issue of timing for a few years. I have now a PhD student who's about to submit her thesis and really fought very badly with it. My general, it's very difficult to do calculation with, to estimate these things from data because you get your sampling of the responses is usually too low, and the amount of additional information you get from timing is not that large. So if your question is whether a neuron can discriminate between two stimuli or not, usually you will get the same answer from timing and count. If your question is how well it can discriminate between what's the optimal performance, if you want to work with optimal bounds and things like that, then you do want to go into the temporal pattern and pay the price. Running experiments like that one, okay, where you repeat each stimulus hundreds of thousands of times in order to get a good sampling of the response. Very few experiments in neuroscience are such that you can really extract time.
שלא הבנתי בכלל איך אתה בוחר את ה-IDD, את כללי ההחלטה.
ה-IDD זה נתונים, אני אומר לך, יש לי אפס.
כן, אבל אני אומר שהראית את שתי ההתפלגויות, שהניורון מתי שהוא יורד ב-100 ומתי שהתפלגות...
experiment design.
מה שהראיתם מקודם שיש את הארבעה אפשרויות בטבלה.
זה נובע מהניסוי. אני אמרתי לך, כשעשיתי את הניסוי, חלק מהניסוי זה שיש לך 0 ו-100. עכשיו אני יכול לבחור 50, 50 ו-500. כשעשיתי את הטבלה הזאת בסוף, אני בחרתי את כל הזוגות האפשריים. אבל בשלב הזה, אז זה חלק
להגיד שבכל המקרים, למה אתה לא אומר פשוט שמ-0 עד 5, מ-0 עד 4 זה יהיה 0, ומ-5 עד 11 זה יהיה 100?
זה יכול, זה אחד מהכללים האפשריים.
אבל כאילו, לא הבנתי אז...
אבל הכלל הזה יגרום לזה שכשאתה אומר 100, הרבה פעמים, כשיהיה 0 אתה תגיד הרבה פעמים 100, וכשאתה תגיד 100 אז הרבה פעמים יהיה תקרא 0.
זאת אומרת, אתה עושה...
הבעיה כאן היא לא, יש הרבה כללים אפשריים.
כן.
השאלה היא, הבעיה היא למצוא באיזשהו מובן כללים אופטימליים. כל הכללים שאני הראיתי לכם הם כללים אופטימליים, במובן שלרמת הקול סלאם שלהם יש להם את הדטקשן הגבוה ביותר.
זאת אומרת שהכללים האופטימליים האלה נוצרים שאתה בוחר אותם לפי היחסים האלה?
כן.
זאת אומרת שאתה אומר שאם יש לך מ-0 עד 4...
כל כללי ההחלטה שלך יש להם את הצורה של לוג C של n בתנאי 100 חלקי d של n בתנאי 0, כל כללי ההחלטה נראים ככה. ומה שזה משנה זה C. כל הכללים האופטימליים, מה שהמשפט שאתם תלמדו בעיבוד מידע ולמידה, זה נקרא הלמה של ניימן ופירסון, אומרת שזה נותן לך משפחה של כללי החלטה שהם אופטימליים ורק הם אופטימליים, והמשפחה תלויה בקריטריון. הקריטריון הוא מה הלייקליות הנמוך ביותר שאני מקבל אותו ומוכן עדיין להגיד 100.
אז בכללי ההחלטה האלה אתה מתעלם מחלק מהמידע? זאת אומרת, יש מידע שאתה מתעלם, או שאתה נותן לו פשוט הסתברות?
אני משתמש בכל המידע, מכיוון אני קובע למשל הכלל, זאת אומרת 9, 10 ו-11 100 וכל השאר זה 0, זה כלל שבו אני אומר שלייקליות של 12 ומעלה, אני אומר 100, כן, כשאני מוסיף את 7 אז לייקליות של 10 ומעלה זה 100.
זה רק במקרה שאתה לא רוצה לטעות.
והכלל שלך הוא כלל שהוא פחות או יותר אומר לייקליות של 1. אני רוצה לחתוך על לייקליות של 1, אבל זה רק אחד מהכללים האלה. שהלייקליות של 1 יכול לגרום לך, יכול להיות, אם המצב הוא סימטרי לחלוטין, אז בדרך כלל לא תהיה סיבה להעדיף לייקליות גדול או קטן מ-1. אז באמת, אבל...
זה לא נובע מהרצון שלך? זאת אומרת, מהרצון שלך לטעות או לא לטעות, בהינתן, להגיד כמה ש...
וחיים מזרק את זה קצת. כשאתה בניסוי פסיכופיזי, אתה באמת רואה אנשים נמצאים במקומות שונים. יש אנשים שחשוב להם נורא להיות תמיד צודקים, ואז הם יהיו מוכנים ב-100, ויש אנשים אחרים שהסכימו לעשות טעויות ב-100, אבל לא לפספס את ה-10. ואתה רואה אנשים באמת בוחרים קריטריונים שונים. הקריטריון של אחד הוא מקרה פרטי, זה מצב סימטרי, אז מה שאתה באופן עקרוני רוצה לעשות, אבל זה לא היחיד. זה לא המצב היחיד.
לא, כי נתת כאילו דוגמה שזה מה שהם בחרו בניסוי, אני לא הבנתי בדיוק אם בניסוי הם העדיפו משהו אחד לגבי השני.
לא, זה אמרתי, אני מנסה עכשיו להשתמש בתוצאות של הניסוי. בניסוי הם פשוט, זה חיה מודמת, פשוט מדדו 21 דרכי ITB שונים, 100 פעמים כל אחד.
כן, לא, אני יודע, אני מתכוון...
כן, כשאני עושה את האנליזה, אז בתור דוגמה בחרתי 0 ל-100, עשיתי בפרטים את המקרה של ה-0 וה-100, אבל אני עשיתי את זה על כל הדוגמה.
וכל פעם ניסיתי למצוא איזשהו זוג אידיאלי, בלי שיש לך אבל...
לא מספיק שלי למצוא שום זוג אידיאלי, פשוט עשיתי את זה על כל הדוגמה. אין כלל החלטה אידיאלי, בניתי את ה-RC curve המלא לכל הדוגמה. כשאתה עושה dual penalty force choice, אתה בעצם גורם לזה שהקריטריון לא ישחק תפקיד יותר. לכן בפסיכופיזיקה לעיתים קרובות אתה עושה dual penalty force choice ולא one time decision. ברגע הקריטריון קובע לך על איזה נקודה נמצא ל-RC curve, אבל ב-dual penalty force choice אתה בונה את הסימטריה לתוך התא, ואז הביצועים שלך הולכים להיות בלתי תלויים בקריטריון, והביצועים של בתוך פורס צ'ויס יהיו שטח מתחת ל-RC curve. זאת הסיבה שבגללה עברתי דרך ה-RC curve. עכשיו, יש המון עבודות ולא סתם שעשיתי את זה, יש עשרות מאמרים היום, ויותר ויותר מאמרים שמשתמשים בטכניקה הזאת. רואים את זה קצת זה בסדר. הפנתה אליי את הגב. Okay, so by the way, the construction of these classifiers, 2, 3, 4 choice and so on, using the ideal observer analysis and all of these things, they became kind of bread and butter of sensory physiology. So they occur in many papers today. You will see a lot of people doing rock analysis at some point in the analysis of neural data. This is what I did was to, in a way, developing informally the proof of something called the Neyman-Pearson lemma that you will learn again in the machine learning Neyman-Pearson lemma. Okay, in statistical theory, which tells you that the optimal decision rules all come from these likelihood ratios when you have a binary decision. Okay, so we talked a lot about single neurons, and we saw that single neurons are actually pretty good. Yeah. Neyman-Pearson. Not quite. I mean, optimal capacity and things like that are asymptotic quantities, and this one is about decisions in the non-asymptotic case. Okay, so, but likelihoods play a role both in capacities and in this log probability thing is. Turns out to be more than just a tool for equalizing ratios which are greater and smaller than 1. Okay, it turns out to be an important way of looking at probabilities. Okay, so here's the question. I showed you one single neuron here. Now suppose that God gave you 100 neurons. Okay. God. So, suppose that you are a student of, you have to design a robot, okay, and you have 100 units that measure ITD, like that are very similar to neurons in real life. Okay, it becomes complicated to say it that way. Okay, so God gave you 100 neurons, and all of them are sensitive to 500 hertz. Okay, and you can decide what is their best ITD. You are allowed to position their best ITDs wherever you want, and what you want to do is to build a machine that would give you the best possible identification of ITD over all possible discrimination tasks. Okay, so how do you do that? Okay, so here's an idealized ITD tuning curve. Okay, that's in this paper they used the parametric form, but the main thing is that this thing has a peak. It has a width that's relatively. It's a significant fraction of the overall relevant physical range between one cycle. Okay, and it has the slopes. And what you see here, this is a bit subtle, so but is important. What's plotted here is this is frequency, this is phase differences, and this gray area represents fixed time differences. Okay, so the subtlety comes from the fact that if you have a sine wave at 100 hertz, then its period is one cycle represents 10 milliseconds. If you have a sine wave at 1000 hertz, one cycle represents 1 millisecond. Okay, so the amount of phase that's represented, let's say, by 1 millisecond is 1 millisecond represents very small phase shift at 100 hertz, but represent a lot of phase shift at 1000 hertz. Okay, it turns out that the relationship is linear. I mean, that's it's easy to see, but again, I leave it to you. Now, this gray area represents what the authors here call the zoological range. Okay, that's the range of ITDs that a cat can observe. It's the same at all frequencies, but here they express it in terms of phase differences. Okay, so a cat head is slightly larger than a guinea pig head. Okay, the largest interoral time differences would be 300, 400 microseconds. So this represents 300, 400 microseconds. At 100 hertz, it represents a very small phase shift. Okay, because the period is 10 milliseconds. Okay, so 400 microseconds out of 10 milliseconds is a small number. At 1000 hertz, it represents a significant fraction, and at some point, it becomes okay. Now, I'll get back to this curve in a moment, but suppose that you are a gerbil at 500 hertz. Okay, so the phase, gerbil has a small head, so at 500 hertz, which has a long period, you will be observing only a very small range of ITDs. Okay, now, as I showed you in the gerbil is like guinea pig in this respect. Okay, they look pretty much the same. I mean, not the animals, but the phenomenology. And what you find in gerbils as well as in guinea pigs is this situation that I showed you where the ITD tuning curves are such that you have a slope within the zoological range. Okay, I showed you data in the previous lesson, in the previous hour. Okay, and the point that they want to make here, the dashed line show you the Fisher information at different ITD values. Okay, it turns out that's the calculation that I skipped. Fisher information depends a lot on the slope. Not only on the slope, but it depends a lot on the slope. Okay, Fisher information is going to be high when the slope is large. Okay, I sort of hinted when I answered your question. Okay, the Fisher information is going to be very high along the slope, and it's going to be small places where the curve is flat. So the dashed lines show you the Fisher information for the blue curve and for the red curve. Okay, and what they want to say is that it looks like in the gerbil it makes sense to position the ITD curves like that, because then you have high Fisher information in the zoological range. Because you have high slopes in the firing rate, okay, you will be able to make good discriminations between nearby values of ITDs when you position your neurons like that. In the case of the barn owl calculates these ITDs also at very high frequencies. Mammals usually use relatively low frequencies for ITDs, but barn owls calculate interoral time differences also at 5000 hertz. Just again, to give you a little bit for a feeling, what's the period of a 500 hertz tone? Physicist. What's the period? How much, one period of a 5000 hertz tone, how much time is it? What? How much? It's 200, no, it's 200 microseconds. Okay, at 5000 hertz, the period, at 5000 hertz, okay, the period is 200 microseconds. Now, the barn owls can discriminate ITD values within this period. They can discriminate, again, something like 1/3 of that. So they can discriminate ITDs that are order of tens of microseconds. Okay, the neurons, the single neurons. This requires very interesting biophysics that, again, we won't have the time to discuss, but there's a lot of work on how barn owls are doing this, using spikes whose width is much longer than the period of these sine waves. Now, So here are what it turns out that in the barn owls you have neurons that have a lot of different ITDs. Okay, and the idea is that each one of them is make the best discrimination at the positions in which its slopes are, and since you have a lot of them, you cover the whole range of possible ITDs. Yes.
But how does this then relate to the size of the head? It doesn't supposed to limit the possible ITDs.
So barn owls and gerbils have heads which are about the same size. Okay, the difference is that gerbils here at low frequencies and barn owls at high frequencies.
But for a certain frequency in the gerbils, why do you have a range that is not
A range of?
a range of the possible ITDs?
Because the sound can come from here and we can come from here. Okay. Okay. So what these people did was the following. They said I have 100 units. Okay. I have the Fisher information curves, and they calculate from these ITD functions, delay functions. Okay. And now they tested all possible, not all possible. I mean, they had a maximization an optimization routine that tried to position the ITDs at different, the neurons, the 100 neurons at different positions, okay, all 100 neurons, each one which is on ITD. They calculated the Fisher information, they integrated the Fisher information within the ethological range, okay, and they looked for the ITD distribution that will give them the highest average Fisher information within the ethological range. Okay, so for each frequency, they solved the problem separately. Yes. So in this, the blue line represents one neuron, this neuron. Okay, the red neuron has the red line. Okay, if you position one neuron here and one neuron here, you have now these two curves which fall within the ethological range, and they summed it up. Why they summed it up? Because Fisher information sums up over independent neurons. Okay. Now here they show you a lot of different neurons. This is schematic. Okay, I will show you the results in a moment. Okay, but the idea is that the difference between the gerbil and the barn owl is that in the barn owl you have a lot of different phases that are. It's 5,000 hertz. You might have a lot of different phases because the period of 5,000 hertz is so short, and that the barn owl will encounter all of these different phase differences, whereas the gerbil at 500 hertz is only a very restricted range of IPDs. That's the purpose of this figure. Okay, so they ran the optimization routine, and what you see here, at each frequency, you see the distribution of ITDs that gave you the best Fisher information within the ethological range. It's averaged across all of their neurons. So this is for the gerbil, and this is for the barn owl. What you get for the gerbils are exactly what we saw. I mean, what you want to do is to position your neurons, half of them on the left side, half of them on the right side. Okay, so that they slope through these are the position of the peaks, okay? This picture tells you that you want 50 of your neurons here and 50 of your neurons here, okay? And this will give you the best average ITD within this narrow region, Fisher information within this narrow region. These are the ITDs, okay, the best ITDs. These are the peaks of your tuning curve, and the fact that you have red here, and blue everywhere else means that you want to put 50 of your neurons here and 50 of your neurons here. You add 100.
Where is the variance?
What?
Where in the graph do you see the variance?
You don't see the variance. That's the distribution of best IPDs in each frequency. That is the solution to the problem. Okay, these are the positions at which you want to put the peaks of your curve. When you do the barn owl, you find these continuous distributions. Okay, these are the ones that optimize the Fisher information. Now, if you go and measure from barn owls and from gerbils, in barn owls you find this kind of, you indeed find a lot of different IPDs. And in the barn owl, in the gerbil and in the guinea pigs, you tend to find these binary distributions, okay, with the best ITD actually outside the ethological range and the slope going through the ethological range. Okay?
What is the color?
Color is the densities, how many neurons you want to put there.
And
Yes.
it all comes from the range of frequencies they hear.
The frequency and the size of the head. These are the two variables. Yeah, so in this case, this ends at 1,500 and this 1,500 is here. So this lower part of the distribution is exactly the same as that one. Okay, except that for the barn owl, which use ITD at high frequencies, they tested also a lot of other frequencies. Okay, now this makes a very specific prediction. Okay, the prediction is that if you will record responses in barn owl for low frequency neurons, you will also see this type of binary distribution of IPDs. Okay, so now this paper caused a war in the community of people who are studying the ITD, and it was people from the barn owl community. This came from the gerbil people. Okay, so the barn owl people got so cross that they actually went and did the experiment. Okay, so by the way.
Is there a lecture here in some seminar that showed this?
Last year, Hermann Wagner was here, yeah, discussed. He was the one who did the experiment in the barn owl. Okay. I always thought this looks like a cat, but. Okay, so the prediction is the barn owls, you will have uniform distribution of best ITDs for high frequencies, but two populations below 3 kilohertz. Okay, and so this is an ITD curve recorded in the barn owl. Okay, again, this goes through 2 cycles. This was done with pure tone, so basically it repeats itself. Hermann Wagner did the experiment. He used actually noise, but not pure tones, to calculate the response as a function of ITDs. But here you see a range of such tuning curves at high frequencies. All of these units have high frequencies, high best frequencies, and you can see the dependence of the firing rate on the ITD. But these are the important results. These are low frequency neurons. Now there's a lot of different neurons here, and what they did was to distribute them by, all of them have best frequencies below 2 kilohertz. Okay, and what they did was to put in each panel all the units that had ITD at a single value. So these are all of the units that had best ITD at about 250 hertz, and these are all the ones that had at 0, and these are at 300 microseconds, and so on and so forth. Okay, so experimentally you get a lot of different ITDs, although these are low frequency units. So this goes against the prediction. One neuron, yeah. Each curve is one neuron. Okay, that's a distribution of best interoral phase differences. So units go from very low frequencies to about 2.5 kilohertz. Okay, and you get a uniform distribution. If you will do this thing in gerbils, you will see 2 lines. Yes. This is firing rate as a function of ITD. Okay, so if I look on the black curve, this is one neuron that I recorded. I used its best frequency, which is somewhere between 0 and 2 kilohertz. I don't know which. Okay, and as I move the ITD from 1,000 to 0 to 1,000 microsecond, one ear leading, to 1,000 microsecond, the other ear leading, its firing rate goes up and then down again. Okay, this is the best IPD. Okay, so now I take this number, okay, and I plot it here at the location that corresponds to the best frequency of that neuron. Okay, and they recorded for many neurons, and this is the distribution. This has come from many animals. Okay, it's not from one animal. But anyway, what you see is a distribution all over the place. So the basic prediction of this paper does not hold. So this is the barn owl prediction that I showed you. Okay, above 3 kilohertz uniform distribution of best ITDs, below 2 populations. This is the result of Herman, and I modified these curves, this plot, so that it would fit on the prediction, and the prediction doesn't hold. Okay, you have a continuous distribution of best ITDs here, which is similar to that one, and not like the prediction. Okay, so it doesn't look like the barn owl is optimized below 2-3 kilohertz in this respect. What? At high frequency, this is what you see. I mean, the point, experimentally, everyone recorded 5 kilohertz. Okay, they put the electrodes so that they go into the 5 kilohertz region of whatever you find in the barn owl, and in fact, behaviorally, barn owls are biased towards high frequency. If you give them high and low frequencies, they would tend to consider the high frequencies more important. Okay, but the question here was whether the low frequencies are optimized for what? In the gerbil, yeah. I mean, okay. So the history goes like that. Everyone believed that this is the way it should be for many years. Okay, this goes back to the 40s and 50s when people started to think about how to use ITD. Okay, and then people started doing experiments in gerbils and guinea pigs, and they didn't find this continuous distribution. They found the two distribution of units, and the barn owl people found that type of distribution. Now, the barn owl people were first, so they were telling the gerbil and guinea pig people, you don't know how to do the experiment. So the gerbil and guinea pig people got angry and eventually collected enough data to convince the world that they are right. Okay, but then they wanted to show that the barn owl people don't know what they are doing. And it goes now back and forth. Okay, the story did not stabilize yet. Okay, so up to here I emphasized Fisher information. There are other ways of quantifying things that are important, that you will find important in papers. For example, you can take the responses and try to actually build a machine that takes the responses and tell you what the ITD is. Okay, and then you can measure things like decoding error. There's something like mutual information. I don't want to go into this right now. The important thing to remember is that all of these things, Fisher information, RC curve, decoding error, mutual information, all of these measures are really measures of signal-to-noise ratio. Okay, the signal is how well the mean of the distributions are separated from each other. The noise is the width of the distributions. Okay, and all of these numbers, eventually, you can trace back their values to these two things. Okay, so when you deal with population of neurons, Fisher information is a nice measure to use because it adds up when the neurons are independent. Okay, this is why you can do calculations of the kind that Nicole Harper and Devin McAlpine did with this issue of how to distribute your best ITDs. Things like mutual information or decoding error are not behave in a very complicated way when you use population measures. But when you use populations. However, neurons are very often correlated. So the last thing I want to discuss is the issue of correlations. And I will use again as an example here a classical experiment. Who doesn't know about this experiment of Bill Newsom, and who never heard about them? Okay. So recordings in awake behaving monkey, The electrodes are in a place in the visual cortex called area MT. Area MT in visual cortex is an area where neurons are sensitive to direction of motion of stimuli. Okay, they are using random moving dots. Okay, so on the screen you have a lot of dots and they move, and they can modify the strength of motion by how many dots are actually moving in the motion direction. The other dots move randomly in different directions. So here all dots move in the same direction. That's very strong motion stimulus. Here 50% of the dots move in one direction and the other 50% are in random directions. Okay, so this is still a very strong motion stimulus. Okay, here there's no correlation. All of them move in random directions. Okay, now the monkey has to report the direction of motion by making a saccade in that direction. Okay, so what they first find the best direction of the neuron, and then they test the monkey by making this, having this motion either in the best direction of the neuron or in the null direction, in the opposite direction. Okay. So it's a behavioral experiment. They can vary the strength of the motion. Okay, how many of the dots, the percent of the dots that move in one direction or the other. Okay, and they can see how well the monkey does, and they get a behavioral curve. Okay, this is from the behavior of the monkey. With very low correlations, the monkey basically guesses. This is 50%. Okay, at 10%, when 10% of the dots move in the same direction and the other 90 are in random direction, it's essentially at the ceiling. It has to make they either move in the best direction of the neuron or in the worst direction of the neuron. The monkey has to say in which direction they moved by saccading, either in one direction or in the other direction. Okay, so if 10% of them move in one direction, okay, the monkey saccades in the correct direction. Either it doesn't matter whether in the best direction or worst direction of the neuron. Okay, it's all basically at ceiling. So, as I told you, 50% correlation is a very strong signal. So this is monkey direction, monkey behavior. Okay, these are spike count distributions recorded from a neuron in area MT. Okay, exactly same spike count distribution of the kind that I showed you in the previous hour. Okay, so they used, these are all the stimuli, spike count direction that come from, spike count distribution that come from, let's start with that one. Okay, correlation of 6.4%, so 6.4% of the dots moved in one direction, the other were random. Okay, the white bars come from those tiles in which the motion direction was in the preferred direction of the neuron. The black bars come from those tiles in which the motion direction was in the null direction. Okay, so you can do the ROC curves and everything based on this distribution and this pair of distribution and this pair of distribution and so on to see how well the neuron would do the same task, and you get curves that look like that. They are not convex, and the reason is that they actually did the analysis in the wrong way. Okay, in approximately the correct way, but not in the correct way, not using likelihoods. Okay, but it doesn't really matter. Okay, if they would have used likelihoods, they would get things that are similar. Okay, so you see, for example, that at 12.8%, you get an ROC curve that is essentially saturated. Okay, I told you a 10% correlation of 10%, the behavior of the monkey is already saturated, and the neuron is wet. Okay, so you can now compare the area under the ROC curves for different strengths of motion. Okay, exactly like we did in the previous lesson, and this is what you get. So each number here is the area under the ROC curve for the corresponding stimuli, best versus null direction. Okay. Now, this was done while the monkey was behaving. So you can actually plot at on the same plot the behavior in open circles and the neuron in black circles. Okay, so this is the beauty. Okay, that's one of the strongest results in the literature. The paper really made a huge amount of influenced a lot thinking about sensory coding, basically because they had a lot of neurons, single neurons that did as well as the behavior of the monkey in that session.
What is exactly the black dots?
Black dots are the areas under the ROC curves. They are derived from this analysis. Okay? So if you look at that neuron, you do as well as the monkey does. And in fact, if you look at the cases in which the monkey did 50%, okay, you can see that the decision is influenced by the number of spikes that occurred in these trials. Okay, so yeah.
I don't know if it's possible, but did they try killing that particular neuron and seeing if the accuracy changed behavior?
You can't stimulate, they couldn't stimulate this specific neuron, but they did microstimulation studies showing that if you stimulate at the location of this neuron, you will shift the decision of the monkey in the direction of the best direction of the monkey, of the neuron. Okay, so they had these results. They had two results. One of them is this one, the fact that this was one of the most dramatic examples of neurometric and psychometric functions corresponding to each other. And they had this manipulation with the micro stimulation. The microstimulation study, they still presumably, they don't know how many neurons they really stimulated, but presumably they stimulated hundreds of neurons. Not millions and not one. Okay, so it's less strong than you would have liked it to be, but okay. So now the question is, going back, why don't you use populations? Okay, so Udi Zohari did his postdoc in the lab of Bill Newsome at about the time that this work came out, and he was asking about correlations. So here is, this is from his paper, the paper that eventually came out. So they recorded simultaneously from one or two electrodes neurons, and they calculated now the correlation. So the correlation here, I have to be careful. They had, in one trial, one neuron fired X spikes and the other one Y spikes. Then in the next trial, they had the spike counts of the two neurons in the next trial, and so on and so forth. The correlation or the correlation between these spike counts. Okay, so what you see here are spike counts correlations. Okay, basically, what they so you have spike counts and you have trial number, trial 1, trial 2, trial 3, and so on. And you have the first neuron firing here, and then 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 here. Okay, and the other neuron, if the other neuron is correlated with that one, it could fire that much in the first trial, and that much in the second trial, and that much in the third trial, and so on and so forth. Okay? So if this one fired a bit more, then that one also fired a bit more. Okay, when this one fired a bit less, and that one, then the X one also fired a bit less. These are the correlations that they are discussed. These are spike counts of one neuron and that of the other neuron. The X-axis is trial number. Okay, so that's first trial, second trial, third trial, and so on. Okay, so these are the correlations that are plotted here. And the point is that there are correlations. They are not very large, maybe. Okay, typical value here is 0.2. Okay, as a rule, if you find in an experiment a correlation of 0.2, you are not very happy. It could be significant, but it's not very large. Okay, so the correlations are not very large, but they tend to be positive. Okay, if you look at neurons which have dissimilar preferred direction, then the correlation is slightly less.